Hello, welcome back. Let's look at the big main part of this section, which is about linear transformations. And we have to define some terminology here. So a transformation, which is sometimes called a map or sometimes simply a function, a transformation T from RC to RR takes any input vector x in RC, so any vector with C entries in it, and gives a unique output vector t of x in RR. Gives you a vector with R entries in it. So this is the same idea as a regular old function, like f of x equals sine squared of x. This takes a number x, and the result, sine squared of x, you say, is the output of the function. And the formula for the function tells you what to do with the input to get the output. Now, the set of all inputs, RC, is called the domain of the transformation, and RR, the set of all vectors with R entries, where the outputs live, is called the codomain. The set of all actual outputs that you get is called the range. So the range is a subset of the codomain. So like, for example, with a function like f of x equals sine squared of x, the codomain here is going to be real numbers, because real numbers are like the kind of thing you get out from this. But the range is just the output values you can actually get by doing sine squared, which would just be the interval from 0 to 1. You're only going to get positive numbers between 0 and 1. So yeah, that range is a subset of the codomain. And the notation, we're going to write T colon RC to RR specifies the domain and the codomain. The domain is the RC, and the RR is the codomain. Let's look at a quick example here with example 3. So here, f is a function or transformation from R2 to R. And what that means is that you can take any pair of real numbers, x1, x2, in the domain, and the kind of thing you're going to get out is a real number. This describes some way of getting some real numbers. So the codomain is all of R. Okay, what about the range? The range of f, according to this definition, is the set of things of the form f of x for some x in R2. So what kinds of things can you actually get? Well, f of x is defined as x1 squared plus x2 squared. And what happens when you square real numbers? You just get a positive real number, maybe 0. Like if your input x is 0, then your output is going to be 0 right here. That's 0 squared plus 0 squared. Otherwise, you're going to get positive numbers. Like if you take x is the point 2 comma 1, then 2 squared plus 1 squared is going to be 5. And that's also true if you take like a negative number too, like negative 2, 1. You're still going to get the same thing when you square negative 2. So the actual range is just all positive numbers, including 0. You just say y is greater or equal to 0 if you want. Write it in interval notation. Doesn't matter. All right, that's a quick example of that. Let's look at example 4 next. So here, h of x is a function that just takes a number x and multiplies it by 3 and multiplies it by 2. So because x is just a number, the domain is R, just a set of real numbers. But the kind of thing you get out as a result of this function has two components, a 3x and a 2x. So that's the codomain, R2. So let's see, what is the actual range of this? Is the range of this all of R2? We can write it on the side here. The range is the set of vectors that can be written as 3x comma 2x for any x in the domain R. And can you get any vector in R2 written in that form? No, not anything. Like, for example, there's no way to get 3, 0 like this, because if you want to get 3x to be equal to 3, then x would have to be equal to 1, and 2 times 1 would give you the point 3, 2. So that's not in the range. But 3, 2 is in the range, 0 is in the range, because you can write that as 3 times 0 and 2 times 0. Likewise, -3, -2 is in the range, or x could be -1/2, and you would get a point about right here. So yeah, you get the idea. Any point on this line is in the range, and that's also known as the span of the vector 3, 2. We're just getting any scalar multiple of 3, 2. So that's the difference between domain and codomain and range. Now, turns out most of the transformations we're going to be talking about are going to be this kind of transformation, where you can write the output as just some matrix A times a vector x. So we're going to think about matrix by vector multiplications, also known as linear combinations, using the terminology of functions. So yeah, let's do the different parts. Let's find t of 0, 1, -2, 0. And remember that 0, 1, -2, 0, that ordered quadruple of numbers is just another way of writing the vector 0, 1, -2, 0. So that's the same thing. And we're just multiplying a by that, like the formula for the function says to do. And we know the definition of this is just doing the linear combination, where we take the entries in x and use them as scalar multiples of the column vectors of A. And if you want, you could always write this like so. But you don't have to. The result comes out to be the vector, where the first component is -pi minus 6, and the second component is -2. So that is t of 0, 1, -2, 0. So what is the domain? The domain is the set of possible input vectors that x can be. Now, what kinds of vectors does it make sense to multiply by this? Well, you have to have 4 entries in x, because you need to have 1 entry per column of A, otherwise A times x is undefined. So the domain is R4 for that reason. So that's the domain. The codomain is what kinds of vectors you get as a result. Now, the kinds of vectors you get when you do a linear combination of these columns is going to have 2 entries, because each of the columns has 2 entries. So you're doing a linear combination of R2 vectors, you're still going to get an R2 vector. All right, now what is the range? The range is the set of all vectors that can be written t of x. But t of x means a times x. So we might as well just write this as a times x. Now remember, the set of all vectors that can be written as a times x just means the set of all linear combinations of the columns of A. That's the same thing as the column space of A, right? That's what we were mentioning back here. Yeah, the column space, the set of all linear combinations of these columns, is also known as the set of all vectors that can be written a times x. Now, what do we know about the column space of this? Well, it depends on how many pivots we have, because if we have a pivot in every row of A, then the column space is all of R. With this one, you could do a little work to row reduce it. We could show that A is row equivalent to this matrix here that has two pivot positions, one in every row, which means the column space is equal to all of R2. So sometimes the range and the codomain are the same, but not always, as we saw in the last two examples. Let's take a quick little break, and we'll come back and look at a lot more stuff about linear transformations.